All of you welcome in our next period, Maths paper 2, set theory and Laplace transformation. First we see some theorems, rules, algebra of inequalities. The first property L1, A is greater than B and B is greater than C. It implies that A is greater than C. Then first is greater than second, second is greater than third, then first is greater than third. Then second property L2, A is greater than B implies A plus C greater than B plus C. That is, if I add C on both sides, we get the inequality as if A is greater than B, then we have A plus C greater than B plus C. Then third property L3, A is greater than B and C is greater than 0, then we have A into C greater than B into C. That is, we multiply by C to the inequality A is greater than B on both sides. We multiply by C on both sides of this inequality A is greater than B, we get AC greater than BC. Then fourth property L4, A is greater than B and C is less than 0 implies AC less than BC. Here is AC greater than BC, here is AC less than BC. Or C is less than 0. If C is negative, then this inequality is same. A is greater than B implies AC less than BC. Here is AC greater than BC. Now see example on this. Let A, B, X and Y belongs to real numbers such that B is positive, Y is positive, B is greater than 0, Y is greater than 0 and A by B less than X by Y, then show that AY is less than BX. We have to show that AY less than BX. We see the solution of this. Consider the given part A by B less than X by Y implies AB inverse, we take B in the numerator, therefore B inverse, AB inverse less than XY inverse. Taking B and Y in the numerators, we get here A into B inverse, here X into Y inverse. Now multiply this inequality by B on both sides. Therefore AB inverse into B less than XY inverse into B. Because by property L3, by this property. By property L3, this property, we have AB inverse into B less than XY inverse into B. Then by associative property, we associate this B inverse and B in one bracket. Therefore, A into B inverse into B less than XY inverse into B, since by associative property. Then we know that B inverse B equal to B inverse into B, 1. Therefore, A into 1 is the identity less than XY inverse into B. Again by property of identity, multiplicative identity is 1. Therefore, A into 1 we have A into 1 A less than XY inverse into B. I am multiplying by Y on both sides of this inequality. Therefore, A into Y less than XY inverse into B Y. Now by commutative property, we write By equal to Yb. By, we write By as a Yb. Then by associative property, we associate Y inverse and Y in one bracket. Therefore, less than X into Y inverse into Y into B. Since by associative property. Again, Y inverse into Y, we know that it is 1. Therefore, AY less than BX. AY less than BX, which is the result that we want to prove. If A by B less than X by Y, then we have to show that AY is less than BX. Therefore, we have proved that AY is less than BX. Then second example we take. Let X and Y be positive integers, then we have to show that X is less than Y if and only if X square is less than Y square. This is if and only if, therefore there are two parts, we have to prove two parts. In first part, we have to prove that if X is less than Y, then we prove that X square is less than Y square. In the second part, we prove that we consider x square is less than y square and we prove that x is less than y. First we prove the first part. If x is less than y, then we prove x square is less than y square. Therefore consider this left hand side, consider x is less than y. Now multiply this inequality by x on both sides. We say x is the positive number which is greater than 0. Therefore x square is less than xy. We multiply by x here, we multiply by y, we multiply by x on the right hand side. On the both sides. Again multiply this by y. Again multiplying this by y, by this inequality by y. Again multiply equation 1 by y. Therefore x into y less than y square. Therefore from equations 2 and 3 we have x square is less than xy and xy is less than y square. Change by 2 and 3. Therefore we have x square is less than y square because first is less than second and second is less than third. Then we have by this transitive property, by third property, by first property L1, A is greater than B and B is greater than C. Then first is greater than third. Therefore we write here x square is less than y square by property L1. Then we prove the converse part. Therefore to prove the converse part we consider x square is less than y square and we prove that x is less than y. Therefore consider the right hand side, x square is less than y square. Now we subtract x square from both sides, from the left hand side in the right hand side. Therefore x square minus x square equal to less than y square minus x square. X square minus x square 0, y square minus x square. Then we find the factors of this. A square minus b square, we know that the factors are given by a minus b into a plus b. Therefore 0 is less than y minus x into y plus x. 0 is less than this, therefore we say that the right hand side is greater than 0. But y plus x is greater than 0. This y plus x greater than 0. Therefore 1 upon y plus x is also greater than 0. Therefore we multiply equation 4 by y plus x inverse. That is we multiply by 1 upon y plus x on both sides of equation 4. Therefore y plus x inverse into y minus x into y plus x greater than 0 into y plus x inverse. Multiplying by y plus x to the power minus 1 on both sides. Then by associative property we associate this to y plus x inverse into y plus x. By this property we have a into a inverse equal to 1. Therefore y plus x inverse into y plus x we have 1. Again by multiplicative property we have y minus x into 1, we have y minus x greater than 0. Therefore we have y is greater than x. Therefore we consider here x square is less than y square and we get x square is and we get x is less than y. Therefore we prove the converse part of this statement. X square is, if x square is less than y square, then x is less than y. This prove the second result, converse part of the example. Then we take the next example so that x belongs to R. which implies x square is greater than or equal to 0. Solution. Let x belongs to R, then we have the three possibilities. As x, from this we can write the possibility x is greater than 0, x equal to 0 and x is less than 0. Three possibilities. X is greater than 0, x equal to 0 and x is less than 0. We consider the three cases. First we consider let x is greater than 0. Now here we have to show this x square is greater than or equal to 0. Therefore we multiply by x on both sides. Multiplying by x on both sides. Therefore x into x greater than 0 into x. Therefore x square greater than 0 into x, 0. X square greater than 0. Since here 0 into x we have 0. Then second we consider x is less than 0. Second, let x equal to 0. Again multiplying by x on both sides. Therefore x into x equal to 0 into x. Therefore x square equal to 0. Since 0 into x equal to 0. Then third, let x is less than 0. Again multiplying by x on both sides. Multiply by x, which is positive, on both sides of this equation. Therefore x into x less than 0 into x. Therefore x square is less than 0. Now if I take x is greater than 0, this is x is less than 0, then we have to use the property number 3. Here we get the inequality changes. We have x into x. Here is x is less than 0, negative. Therefore we have by property x into x is greater than 0 into x. This is by property L4. Since by property L4. Again x into x, x square is greater than 0 into x, greater than 0. Therefore considering all the three cases, we have x square is greater than or equal to 0. We get x square greater than or equal to 0. This proves the result. We have to show that x belongs to R implies x square is greater than or equal to 0. X square is positive or equal to 0. We try to solve this. Let x a belongs to R. So that a is positive. Then show that a inverse is greater than 0. Then show that a inverse is positive. Try to show.